Gotta wait for the microphone, sorry. We'll go ahead and get started with our first speaker today. So I'm going to introduce Leah Johnson, who you all met yesterday as well. Leah is currently a postdoc at Brown University. She did her PhD at University of Washington. She's been working on mixed layer dynamics, and she did that from an observational perspective as a PhD student, and now she's doing it from a modeling perspective. And so she'll be talking to us about one-dimensional mixed layer models.
All right. So I sit at this intersection between observations and models, and I think that's a really cool place to be. The mixed layer is what I focus on. It's a really dynamic place, as seen in this schematic by Megan Cronin's paper in 2001. So first, I'll just kind of define what a mixed layer is. It's usually near a boundary. There's both surface mixed layers and bottom mixed layers, but we're going to be talking today about the surface mixed layers. And because they're at the surface, they're subject to a certain type of forcing. We have forcing of heat and fresh water and also momentum that can dictate the amount of turbulence that is occurring in the boundary layer, which can be mixed down to different depths. And so this causes mixing and is going to homogenize tracers in the upper ocean. So if we look at a density profile, so we have the mixed layer and then the deep, kind of relatively quiescent ocean underneath. And the mixed layer is going to be turbulent, and it's going to mix down, or mix up, I should say, temperature and salinity and therefore density. So you get this constant density followed by a stratified interior where density is increasing. And I should mention that it's usually homogeneous in tracers, not necessarily momentum, and we'll see implications for that later. So because the mixed layer is forced at the surface with surface forcing and winds, it can tend to have vary in both space and time. And this is a plot of mixed layer depths from ocean climatology, the MIMOC climatology, taken in 2 different months for January and July. And you can see both the seasonality. Here we have really deep mixed layers and not very deep mixed layers, deep mixed layers. And I apologize for not picking months that highlight the seasonality of mixed layer depth in the Bay of Bengal, but there is a seasonality there, and but we can see from these images that generally the mixed layer in the Bay of Bengal is pretty shallow and compared to other regions of the ocean, and that can have some large impacts on the air-sea interaction. So one reason why I really like mixed layers, there's lots of reasons why we should care about it, but the mixed layers are interacting with the atmosphere and take up heat and buoyancy and fresh water from there. And these waters can sink down into the ocean interior, either through deep water formation or mode water formation. And this carries with it the signature that was imparted at the surface. And so it's going to carry temperature and salinity signatures throughout the water. And the density that it has when it sinks is going to dictate its future of how it is going to move through the general circulation of the ocean interior, which is pretty cool. And so if you take a profile, these are profiles of temperature and salinity from the MIMOC climatology, taken at various places in the Bay of Bengal. And so at the surface, we see temperatures and salinities that are characteristic of the Bay of Bengal. But as we move deeper, we find water masses that were once at the surface someplace else, either in the Arabian Sea or came through Indonesia. And these are all temperature and salinities that were characterized when those water masses were at the surface. All right, and so another reason why we might care about the mixed layer is because it regulates the uptake of carbon and also biology. And so biology cares about being close to the surface, so they're going to care about the mixed layer. They want to be close to the surface where they can take in light, but they also care about entrainment at depth, because entrainment is going to bring up nutrients. And so this is another reason why we care about mixed layer depths. All right, so Even though the mixed layer is a very ubiquitous thing that we talk about in the ocean, and we care about it a lot, there's actually no consensus on how we define it. And so a more general way is to use a temperature or a density criteria. So you just take the difference of density at a reference depth, mostly the surface, and you say when that exceeds a certain value, that's the depth of the mixed layer. If you care more about dynamical processes mixing, you might use something like an entrainment buoyancy flux at the base of the mixed layer to define what that is. Or a maximum in stratification. And so these are subtle differences, but depending on what you care about in the mixed layer, you might be seeing people using different definitions. And because of this, there's also really no consensus on how people actually talk about the mixed layer depth. There are people who talk about turbulence who don't really like using mixed layer, and they like to use something called the boundary layer. And people don't really like the boundary layer, so they say the well-mixed surface layer. And so this is just to highlight that as you're reading through the literature about these things, you might be seeing different conventions, and they're essentially talking about the same thing, but there's going to be subtle differences in what they're actually trying to capture. All right, so what controls mixed layer depth? Well, like I said, it's going to be a competition between the stratifying effects of buoyancy input due to warming and freshwater fluxes, which are going to make the water lighter and inhibit mixing. And then we also have a competition against deepening effects due to surface cooling and momentum input from the surface winds. And this is going to act to entrain deeper waters and enhance turbulence. And I also included in here the re-stratifying effects due to lateral processes. So this might include lateral advection, or three-dimensional processes such as eddy restratification, which can be extremely important on the time scales that the mixed layer evolve and should be considered, but are not in these 1D models. And then also the deepening effects of surface waves, which are really efficient at driving momentum rapidly down to the mixed layer base and can encourage enhanced mixing down there. And that's something else that is rarely captured in these one-dimensional models, but is something to consider. All right, so Emily went over this yesterday, but it's always good to go over it again. When we're talking about buoyancy forcing at the surface, we have both buoyancy input from the heat flux, surface heat flux, and from evaporation and precipitation. And in terms of heat flux, we have shortwave radiation, which is going to warm the ocean, and long-wave latent heat and sensible, which for the most part tend to cool the upper ocean. And when the upper ocean cools, it can cause destabilizing surface conditions, which cause convection, and the convective scale, velocity scale is W star, which depends on this buoyancy forcing and the depth of the mixed layer. So the other piece of this story is going to be momentum input from winds. Based on the wind speed is going to impart a surface stress. And again, like Emily talked about yesterday, this is going to result in Ekman dynamics, where basically surface forcing, horizontal forcing is going to be translated down into the mixed layer through viscous terms. And this is creating horizontal shear, and that shear can ultimately enhance mixing in the mixed layer. And this can be captured in the turbulent velocity scale, U star, which depends on the wind stress. So the relative importance of buoyancy forcing and wind forcing can be captured in the famous Monin-Obukov length scale, which is based on U star and W star and includes the von Karman constant. And this basically says, given a certain amount of wind and buoyancy, you can estimate what the length scale of turbulence should be in the water. And this has really been an important application for both ocean and atmosphere boundary layer dynamics. But the subtle thing about this is that it doesn't take into consideration the vertical structure of the water column. And so why should that matter? And the best way, I think, to describe this is in terms of energetics. And so if you have a water column that has a certain density, stratification. It's going to be low light water up here and dense water down below, and this is having a certain amount of potential energy. And as you input kinetic energy into the system, you're mixing up the water, you're bringing up cold water to higher up in the water column, and you're increasing the potential energy. And so the amount of cold water that you're going to be able to bring up is going to be dependent on how much kinetic energy you're inputting into the system. And so this is going to ultimately factor into how deep our boundary layer mixing can be. All right, so in order to do this, what do we have here? We have a density profile, and we're going to add momentum, and we're going to add buoyancy, and we want to see how this is going to change in time. That's basically what our mixed layer model is going to do. So we're going to need some sort of tendency equations for density and momentum in order to have a mixed layer model that's going to predict what's happening in the upper ocean. So we're going to start with our governing equations that have been simplified to this state, which is horizontal momentum and scalars. And we're going, mainly, I'm going to leave this as C, but we're talking about T and S here. And a lot of assumptions can go into this. We're going to ignore the advective terms. This is a 1D mixed layer model, so we're not going to care about things coming in from the side. So our material derivative can just be come1 in terms of T. We're going to say no horizontal pressure gradient. That term is going to go to 0. And for now, I'm just going to take this complicated mixing term, and I'm going to just say it's T flux for now, and we're going to talk more about that later. So our equations become this. This is our 1D model. We still have our Coriolis term, and when these two terms balance, we get waves. This is waves, but we have this turbulent term here, and we also have this scalar form. And what's interesting about these equations, this is a 1D model, so we care about information going up and down our 1D model. And the only term in this equation that cares about that is going to be this T flux term. It's going to be this turbulent flux of momentum or turbulent flux of scalars. And so this actually ends up being a really important part of our 1D model. It's also the most difficult part of our 1D model to manage, and is the one thing that in my mind, each 1D model is approaching this, how to approach this term differently, and that's going to be essential in the characteristics of this model, these different models. So what are the ones that we're going to be talking about today? We're going to be going over the Price-Weller-Pinkel model, the PWP model. This is a bulk mixed layer model, so it treats everything in the mixed layer as just one, like averaged out in temperature and momentum and salinity, and therefore this T flux term is going to be set at the boundaries. And then we're going to talk a little bit about KPP, the K-profile parameterization by Large et al. And this uses empirical formulas to estimate the depth of the boundary layer. And then also, what it really is doing is it's taking this T flux term and it's converting it to a form that uses eddy viscosity. And so the entire KPP parameterization is designed to estimate this K. And so this K is going to be used in our equations in order to step them forward in time. And I'll be going over that. And then I'm really not going to be talking too much about TKE models, total kinetic energy models, but they're a huge branch of boundary layer mixing models, and so it's at least worth mentioning them. All right, so the Price-Weller-Pinkel model is a bulk mixed layer model, and so it really treats the entire mixed layer as one huge layer, and so all of these terms are going to be averaged over the mixed layer depth, and therefore the turbulent terms that come into this are going to be set at the surface averaged over the mixed layer. So for example, momentum, we have the input of surface stress, which is averaged over the mixed layer, and the same with heat flux and buoyancy. So the key here is determining what H is, and Price-Weller-Pinkel has PWP has a system for doing that. They basically check 3 different criteria. This is, by the way, the 1D mixed layer modeling group is exploring PWP right now, so you're going to be hearing more about it throughout the week. What? Oh, it's E minus precipitation. I could have done EP or something, but it's evaporate. Yeah. What? Does capital H vary? Yeah, so that's exactly the trick of this, and we're going to talk about that. Yeah, it's like the subtle part about this, because you need to define what H is. And so PWP does that iteratively, and so it checks the first thing it does is it checks to make sure that the mixed layer is stably stratified, and it goes through every single grid point to make sure that it's stably stratified, and if it's not, it will mix down to a depth where it is, where this criteria is met. And then there's a momentum mixing criteria. So again, it goes through and it takes this value of density and velocity and a value at depth and decides at what depth is this criteria met. And then it chooses that as the mixed layer depth. And then there's another third criteria, which is another Richardson-based criteria, but it's just kind of mixing locally, and this is kind of to smooth out gradients, particularly at the mixed layer base. And so what's happening is H is determined based on when these criteria are met, and then it uses that H to integrate the equations forward. All right, so it uses this H to step forward and evolve our fields. All right.
It's as if some of these criteria do not depend on the boundary conditions at the top. They worry about when the changes.
Yeah, I mean, you put, right, so it's a little bit of a chicken and the egg, but you put in the boundary conditions, you step it forward, and then you meet these criteria, and then you go back and you step it forward again with the H, but with the new surface forcing, and then, yeah, so, but yeah, it ends up fitting in there. All right, so PWP, the one I should mention, the one really nice thing about the PWP model is the modeling group is going to find out this week is that it's quite user-friendly. Every step is clearly defined, and it's widely used among the community because of that. There's a model that gets passed around. You can open it up. You can see what the terms are doing, and it gives people reassurance that they understand what's going on in their model. And so it can be really user-friendly. The K-profile parameterization is another 1D mixed layer model that's widely used. This tends to be used in global circulation models or more complicated 3D models like the MIT GCM, and it also kind of treats the mixed layer in a bulk sense, and therefore it's very numerically efficient. But it's trying to be a little bit more precise in capturing the behaviors of turbulence in the mixed layer. And so it's going to take this turbulent flux of momentum and turbulent flux of scalars term, and it's going to define it using an eddy viscosity. So, and this is K. This is the K in the K-profile parameterization. So this entire parameterization is based on defining this K. And this is a profile of K. You can see that it is 0 at the top and bottom of the boundary and has this curve, which is maximum somewhere in the middle of the mixed layer. And there's a local component. Another feature of the KPP parameterization is there's a local component, which says, all right, if you have what's happening locally, how is information being transferred right above and below me, and how is that going to change what's happening? But another thing that it has is this non-local component, and this is because during, for example, destabilizing surface conditions, you can have these convective plumes that are taking water from the surface and bringing it all the way down to depth and then all the way up to the surface. And that's clearly not a local event, that's a non-local transport. And so particularly during destabilizing conditions, we can get this enhanced diffusivity, and that's what that's capturing. It's generally captured in terms of scalars. Some people are exploring what that looks like in momentum, but I've left that gray for now. Right, and so this is what the equations end up looking like. We're going to be stepping forward these equations with these eddy viscosity terms. So the trick here is determining what K is, and the first thing that KPP does is it determines the boundary layer depth. And this is dependent on a Bulk-Richardson number. This is starting to look very similar to a Bulk-Richardson number that we saw in PWP. So you take the buoyancy difference or density difference from the top and the bottom of the profile, and a velocity difference from the top and bottom of the, or different layers, and you decide when that reaches some sort of critical value. There's this addition of an entrainment term, which also becomes enhanced during destabilizing surface conditions, and that's just to help capture entrainment at the bottom boundary. And when this criteria is met, you say that that's going to be the boundary layer depth. And then a combination of the boundary layer depth and the Monin-Obakov scaling that I mentioned earlier, which depends on U star and W star, our friction velocity and our convective velocity, are going to be used to come up with a bunch of constants that are going to allow us to determine a shape function for our viscosity profile. So this is all empirically devised, and so the model kind of takes care of this. I'm not going to go into the details now, but one thing to notice is that the shape function, which is G, is a polynomial, and that's what's going to set this curvature. So the characteristic of the KPP profile is that parameterization is that it's always going to have this sort of shape function to it. And then now we have this this kappa, and we're going to, and then we decide what the non-local fluxes are, and then we can use this in order to step forward our equation and evolve it in time. So that's KPP in a nutshell. And like I said, there's, it's bulk, so it's very numerically efficient and very friendly for large models. All right, so another very common way to approach mixed layer dynamics in the ocean is to use a total kinetic energy approach, a TKE approach, and I'm not going to talk about this here, but it's a huge part of the literature. There are many different ways to do this, but basically you're taking the viscous terms, you're using Reynolds averaging to come up with an approximation for what that term should be. A famous one or a popular one is to end up with second moment terms for W and W prime U prime and W prime C prime, and then use solve for these terms using a TKE approach and moving the model forward in that way. And this is very popular for people who care about specifics of mixing near the surface or near bottom boundary layers, and is used also in the engineering community, not just ocean community. But one thing that I plotted here was the effective viscosity from calculating this in a TKE type model. And you can see that it has a structure very similar to the K-profile parameterization, where you have a maximum in the middle of the mixed layer. But this is not empirically derived. This is solved using physics in the TKE approach. But it's a little bit different. You can see that there's this kind of kink with a little bit of viscosity, maybe right below the mixed layer base. And so this has implications for how it's moved forward. Yeah, you want, well, like high frequency in what sense? Like, you need, I think you need like pretty good time resolution in order to resolve something like this, so you can't use very large time steps. No, you usually need a pretty high resolution model with a time step to be able to resolve these. Oh, you're not calculating it directly, you're inferring it through other physics parameters. Yeah, that's a good point. Yeah, you're not calculating. This is still ultimately a parameterization. So you're still coming up with a way to an approximation for these terms, but it's using physics within the total kinetic energy equations instead of empirically deriving it like KPP does. Yeah, good point. So there are two sides. There are people who say that this is the way to go, and if you look at some case studies, they say that the TKE approximation is what you need in order to resolve, for example, stratified turbulence near boundaries or bottom boundary conditions. And then there's another group of people that say, oh, well, TKE approaches don't get convection right, and they deviate in that way. And I think, the work that I'm doing now, it shows that these really do deviate, and we don't really know what truth is, and that truth might depend on place to place. So, but each of these have been compared in some sort to observations and agree to some point. Mm-hmm. Yeah. All right, so we're going to now get a chance to see how these different models compare with each other. And I've chosen a example that is kind of inspired by the cruise that was last summer in 2008 that some of the data analysis groups are going to be using. So this is in black, this is Bay of Bengal, sea surface temperature from climatology, and here's the cruise track in black. And I've taken a climatological profile in the middle of this track, and I forced it with reanalysis. So this is an example of the surface forcing from reanalysis here. I also have winds, and this is a pretty relatively smooth profile that is climatological. More complicated, realistic profiles will respond differently, but and the modeling group will see that, but we're just going to use the smooth profile right now. And so I'm going to play this movie, but let's first get ourselves oriented. In the upper left-hand corner, we have heat flux, and there's going to be a little bar that's going to step forward in time to show us where we are. And then we also have a wind stress that picks up and then starts to decrease again. And here we're looking at temperature profile. This is the initial profile, a profile of salinity, and it starts with 0 U velocity. I'm not showing the V velocity, but you'll get the point. And maybe I'll play this twice. And so as we move forward, and the one thing that you'll notice immediately is that the ocean sets up with a velocity that has inertial oscillations that start going back and forth. And the mixed layer starts to deepen. We get cooling, which deepens the mixed layer. And it's entraining salt water from below, and so it's getting saltier. You'll notice that the PWP, which is in green, that momentum is homogeneous throughout the mixed layer, but for KPP and K epsilon, you end up getting shear, enhanced shear, both at the base and at the surface. Let's play that again. This is about 2 weeks. And again, we're starting to see a deepening of the mixed layer. It's cooling, and this is consistent with what was seen in the observations, a deepening and a cooling of the surface waters while the ship was out there. So this is at least going in the right direction. But notice that each model is just a little bit different. You can see that they are producing different mixed layer depths that are about 10 meters apart towards the end, most clearly seen in the salinity profile. So even within these 2 weeks, you're starting to see a divergence in agreement between these models. For this case, I've plotted the mixed layer depth, temperature, and salinity. And we can see that even though there's a variation in these mixed layer depths, temperature and salinity aren't that, they start to deviate a little bit, but I guess depending on what you care about, you have to estimate how much you care about whether or not those deviations impact your results. But it's something to take into consideration. And this is all based on different physics that is ultimately causing these deviations to occur. All right, so I've summarized a couple of common 1D models that we find in the literature that are used by the community. But what are they used for? And so I thought I'd highlight some examples. And I like to divide them up into two groups. One is using 1D processes, 1D models to understand 1D effects, so the effects of wind and buoyancy forcing in terms of heat content or momentum. And another is to use 1D, like if you're comparing 1D models with observations. And another idea is to use a 1D model and compare it to observations to talk about the importance of lateral processes. So things that aren't captured in a 1D model. So you're really contrasting the models and the observations in order to highlight the fact that these dynamics are important. And I'll step through some examples of that. So 1D for 1D purposes, examples I'm just going to take from the Price-Weller-Pinkel model, although you can find this ubiquitous in the literature. But you can force your one-dimensional model, and then you can look at the evolution of velocity in your mixed layer, and you can look at what's called a hodograph, where you're plotting U and V velocities, and you can see that the model is able to produce similar structures of time evolution of velocity in the mixed layer, and then also in terms of the vertical structure. And you can also use a 1D model in order to estimate the amount of heat content that is going into the ocean, and you can compare it with your temperature profiles and say, yes, that the ocean is taking up this much heat for this much reason. It's also widely used beyond physics approach and used by the chemistry and the biology community. Here's an example of a DIC budget. So someone wants to know how much carbon is entering the mixed layer, but you can't just set your H constant, because that's going to be an unrealistic reservoir in your budget. And so you want to be able to vary H. And to do that sensibly, you can use one of these 1D mixed layer models, get a time evolution for H in order to get a more accurate budget for your carbon content. And the same can be done for oxygen. If you want to know how much oxygen is getting inputted into the mixed layer, that's going to be dependent on how big H is, and so you're going to want to have a sensible number for how H is evolving. All right, another very common approach is, which has been used by me and many others, is to use 1D models and contrast them with observations. And here are some examples. This is from Jared Buckley, and he's going to go over these results later today in the T-Talks, but I thought they were really nice and wanted to include them. What we're looking at is a time evolution of temperature from the Hui boring in the Bay of Bengal, and these are different one-dimensional models, and he uses different techniques in order to estimate advection, the role of advection. And when you do that, you're able to better estimate, when you add advection in here, you're able to better estimate what's going on at the mooring. So it's highlighting the role of advection. This is another paper taken from the Gulf Stream, where someone uses a 1D model and compares it with observations of an eddy passing through. So an eddy passing through is most definitely not a one-dimensional process. So they say the 1D model, and then they show the eddy passing through, and they say that this difference is really important for impacting the temperature and salinity that is going to cause mode water formation in this region. And so again, they're contrasting the lateral advection with this 1D model. Another important feature of mixed layer stratification is this eddy stratification. So there's the mixed layer is full of horizontal features, and those horizontal features can cause eddies that enhance stratification in the boundary layer on pretty significant time scales. And this is a pretty seminal paper by Mathur et al. In Science in 2012 that compared a model with and without this feature in order to show that it's important for enhancing stratification and therefore enhancing the phytoplankton bloom in the North Atlantic. And then similarly, I've used TS structures globally compared with one-dimensional models in order to look at the effect of these small fronts and how they can impact stratification in the mixed layer. So again, I'm using a 1D model and contrasting them with observations and the temperature and salinity structures in order to find this. So these are different ways. You don't only have to think about 1D dynamics in order to use 1D models. And that's pretty much it. So I wanted to conclude with some closing remarks, and that's to highlight that these 1D models are very useful. Besides being implemented into larger more complex circulation models, they can be used as standalone in order to understand both 1D and non-1D dynamics. I hope that by showing you the differences between these models, you start to get a sense that each of these models have their limitations, and that's just something to consider when you choose a 1D model and decide to use it. But mostly, they're a lot of fun, so have some fun with it. All right, thank you. So I started a little, yeah, go ahead.
Can you say something about the mean shear? Basically, you have this mean shear seeming to go with the sun rather than with the wind stress, at least in your movie.
Yeah, so it's not solar, it's going to be inertial. So, I mean, it's almost solar because the inertial frequency and the solar is equal. But if you were to plot it up, it's actually going to have a frequency corresponding to 2 pi over f.
So where in your model does it come from?
It comes from the f term in the momentum equation. So you have this. Let's just get to one of those. So you have this du dt and fv. Yeah. So this is your inertial oscillation, and we're going to learn that in Manny's talk in a second. Basically. Sorry to give it away, Manny, but basically, this is your wind-forced inertial oscillation.
Length scale you defined based on buoyancy and the force.
Wait, say that again?
When you go back to that length scale you defined based on buoyancy and the wind stresses, there was some length scale you defined.
Oh, the Monin-Obakov?
Yeah.
Yeah.
So how is that related to the typical Ekman length scales that we have? Like, are they related in some sense where this flip happens of the U profile?
How is
that length scale related to the Ekman, typical Ekman length scale where the flip happens?
Right, so...
are they related in...
Like, how does this compare with the mixed layer that a model will produce? Is that what you're asking?
Yeah.
Yeah, so for example, this usually tends to be deeper. So, so in KPP, for example, they check their, like, you can never have a mixed layer depth that's deeper than Monin-Obakov. And so Monin-Obakov is generally considered a limit of, an upper limit. And that's a good question. I think it's if you're questioning some sort of thing in your model, maybe one thing that you want to do right away is compare it to the Monin-Obakov and see if maybe you're having a numerical instability or if something's not right with the surface forcing, because this should always set the lower bounds. Yeah, and these ultimately feed into all of these models. Even the TKE model approach cares about the turbulent and the convective velocity scales. All right, I think we're done.